So today we are continuing our discussion involving NRTL flash calculations. In the last video, we had done a constant pressure, constant temperature flash calculation for which we had outputs of our vapor mole fraction, our liquid phase compositions, and our vapor phase compositions. As we can see here, we have our outputs as I had defined earlier, and we can actually use these outputs for something that's called an adiabatic flash calculation. And an adiabatic flash calculation, most reactions generate heat, so our goal for an adiabatic system is to make that change in heat zero. So if it's an endothermic reaction, we want to heat our system so that that heat stays constant. Vice versa for an exothermic, we would be cooling that system. And so when we do that, we are talking about a function. So flash NRTL. We're talking about a function that has inputs of our composition. We have some sort of feed enthalpy for our reaction. We're going to have a flash pressure. And we are going to have some Q, which is our heat. And that's going to be equal to 0 because we do not want to generate heat in our system. So this flash pressure is different from the feed pressure, which we had defined as atmospheric here. So you can see that we have our atmospheric pressure, that's going to be our feed pressure. And we have a flash pressure, which is the pressure within our actual flash drum. So these two pressures are going to be crucial in defining our flash system. Before all of this, though, I'm going to initiate our feed enthalpy and initiate the calculation for that. So first we want to figure out what our feed temperature is going to be. And that feed temperature, we're going to say, is our bubble temperature using our NRTL model. Our composition is going to be our Z's, our equimolar mixture of isopropanol and water. And we're going to have just our feed pressure. And we just want to grab the temperature component of that. So that should give us our feed temperature. Now the next step is we're going to want to calculate our feed enthalpy. And our feed enthalpy is just going to be our feed rate, which we have defined as 1 mole per second up in this very top cell, times we can actually pull from our CHE5 notebook, from our props library, our properties. We can actually pull the liquid enthalpy of our mixture using our composition and our feed temperature. So this calculation here should give us our feed enthalpy. So our next step, I'm going to implement another function here, and we're going to name this our energy balance, and you'll see why in a minute. For the inputs, we need some flash temperature, which is something that we don't know quite yet, but we can use this function and a root solver to get that flash temperature. So the first thing we can do is I'm going to actually unpack this flash NRTL into our phi, our x, and our y. And I'm going to have that equal this. I need to cut that out. So now we have our phi, x, and y to work with. So what we can do is we can calculate our liquid enthalpy first. So our liquid enthalpy is going to be equal to our feed rate times 1 minus our phi, because phi, remember, is that vapor mole fraction. So this is going to be our liquid mole fraction for our liquid enthalpy, times the liquid enthalpy given our liquid mole fraction compositions and our temperature, so our flash temperature. And then the same thing goes for the vapor enthalpy. and that's going to be our feed rate times just phi times our vapor enthalpy. So we're going to have inputs of our Y and the flash temperature. And then what we want to return is going to be our liquid enthalpy plus our vapor enthalpy minus our feed enthalpy minus our Q. And if we return this and we set this target function equal to 0, we should get the flash temperature that satisfies this function. So now we can go ahead and we're going to calculate our flash temperature using our optimized root. So scipy.optimize.root scalar. We're going to target our energy balance. But before I move on, instead of using the Newton method, I want to use another method, which is the bracket method. So what we're going to do is we're going to have a bracket, and we have to give it a range that we want our final solution to be between. Well, we want our flash temperature to be between our bubble temperature at the flash pressure and the dew pressure at our flash pressure, or the dew temperature at our flash pressure. So we can actually calculate these beforehand. So let's go bubble T at flash P. That's going to be our bubble temperature using our NRTL model, given our composition, flash P. And it's going to be at first, that first value that gives us our temperature. We're going to do something similar for the dew temperature, or the flash pressure, equals dew T NRTL composition flash pressure, and then we just want that first value. And actually what I'm going to do here, because I think I also realized a mistake that I made. So what I'm going to say here is I'm going to define a flash pressure, and our flash pressure is actually our atmospheric pressure. So we'd be feeding at a higher pressure than our flash drum is at. So our flash pressure is going to be atmospheric. Our feed pressure is going to be 200,000 pascals. So now calculate that. And so we want a bracket. We want that to be between our bubble temperature. So between bubble T flash P and our dew T flash P. So this is the range we want our final solution to be between. And we just want to pull the root of that. That'll give us our flash temperature. And then given that flash temperature, we want to recalculate our values using our PT, our flash PT. So now we will reconstitute our phi, x, and y. So flash NRTL PT, and at this point we're going to be using our compositions. We'll be using our flash pressure and our flash temperature. And then finally we will want to return our flash pressure. So our flash temperature, our phi, x, and y. So let's go ahead and let's give this a go and see if we converge. PQ. Have our compositions. We have a feed enthalpy, feed H. We we have a flash pressure, and we have a Q. Or I guess we might not need a Q since we already have 0. So my mistake actually lies within this feed temperature. If you remember, we redefined our feed pressure here, and our feed temperature must align with our feed pressure, obviously. So this should be our feed pressure. And now if I run this, we see that we get our flash temperature is around 353.73, and we have our vapor mole fraction, we have our liquid phase compositions, and we have our vapor phase compositions. So that is a successful line of code for us to be able to determine our phi, flash temperature, x, and y, given our compositions, our feed enthalpy, our flash pressure, and our adiabatic requirements.